Next, we're going to take a look at factoring a function completely, given as complex 0 in this case. So notice this says option 1. I'm going to run through two different examples with two different ways of finding all of the zeros. So the first option is similar to what we did yesterday with the rational root theorem, and that's using synthetic division. So I'm going to set that up with my coefficients and my 0. Now I was given the 0, I wasn't given it in factored form, so I use exactly the 0 I'm given. If you forget and you use the conjugate, you're going to have to repeat it with the conjugate anyway, so the order really doesn't matter. So bringing down the 1, multiplying by 1 minus 3i, adding these. Now make sure you add your real part to your real part, so negative 3 plus 1 is negative 2, and there was no imaginary part to add it with. Now, when I multiply this by my 1 minus 3i, I'm going to have to FOIL. So you may need to show some work. And we get negative 2 minus 3i plus 6i plus 9i squared. So when we combine our like terms, that 9i squared is really a negative 9 with the I squared being negative 1. So I have negative 11 plus 3i. Combining that with my 6, again, make sure you're adding those real parts together, and now I have some more FOILing to do. So 1 minus 3i times my negative 5 plus 3i, and I get a little more room to work here. So combining my like terms, that negative 9i squared is really a positive 9, plus 5 is 4, plus 18i. Adding that to my 2, I have 6 plus 18i. And one more time, I'm going to have to FOIL. Alright, so notice that my imaginary parts cancel, which is exactly what you want because you want a remainder of 0. So I have negative 54i squared, which is really a positive 54 because I squared is negative 1. Combined with my 6, I get a 60, which gives me a remainder of 0, which is exactly what should have happened because I was told that this is a 0 of the function. So after we do all that, we need to repeat this process with the conjugate. We've got to get all of those I terms out of there in our final factored form. So I'm going to erase my work so I have room for my next work. And I'm going to divide this by the conjugate 1 plus 3i. Bringing down the 1, multiplying by 1 plus 3i. First couple of steps don't take so long. Notice our imaginary parts cancel. That's exactly what we need to have happen in order for us to get a polynomial left that we can factor normally. So this one won't be quite so much work as the next one because now I can just multiply by negative 1, which is a lot simpler than FOILing those imaginary numbers. Again, notice my imaginary parts cancel, so I get negative 6. Distributing that, I get negative 6 minus 18i. My negative parts cancel, and my real parts cancel. That was the last term. If I didn't get a remainder of 0, it wouldn't be a factor, and I was told that it would be a factor because imaginary roots always come in pairs, the pair being the conjugate. So now I have x minus 1 minus 3i, x plus, sorry, that should still be a minus, x minus the conjugate 1 plus 3i, and here this result, x squared minus x minus 6, which I can factor using the t-chart method. So this is the beginning piece to finding all of the zeros of the function. So we know the two imaginary zeros, 1 minus 3i, 1 plus 3i, and we just need to factor this last piece, x squared minus x minus 6, which we saw in a recent video, I think it might have been yesterday's video, how that factors using the T-chart method. So all of the zeros, 1 minus 3i, 1 plus 3i, and those last two pieces that we found when we finished factoring, 3 and negative 2. So notice this was option 1. Some of you may prefer the synthetic division. Yes, that first piece takes a little bit of work, but once you get that first piece done, the second synthetic division goes fairly quickly, and then you can do T-chart or other factoring methods. The next option, notice it's the same question, so we're going to find the same zeros using a different method. First is multiply your imaginary roots together. So those would be when I wrote them in the factored form, and x minus its conjugate. So we're going to multiply these together first, and then we're going to use long division. So when I multiply these, I first of all distribute the negative sign, and then I use my box method anytime I'm multiplying more than a binomial times a binomial. I'm just going to use that line for convenience. So we've got x minus 1 plus 3i and x minus 1 minus 3i. So multiplying this hopefully quickly. All right, and simplifying this, those imaginary parts should cancel. So we get x squared, negative x minus x is negative 2x, 3xi cancels with negative 3xi, 3i cancels with negative 3i, negative 9i squared is really positive 9 because I squared is negative 1, plus the 1 gives us 10. So this is the factored form of those two imaginary roots. So again, we're going to set this up using long division to finish factoring. And put the x squared minus 2x plus 10 outside. So again, I'm showing you two different methods, so you can choose the one that you prefer. X squared times x squared gives us the x to the fourth, distributing that to all of the pieces. And when you do your long division, make sure that you subtract. I highly recommend, in fact, I insist that you change the signs so that when you do your subtraction, you're actually adding, which is much easier to keep track of. So we got a negative x cubed minus 4x squared, bring down the 2x. X squared times negative x goes into the negative x cubed, distributing the negative x. And again, change the signs so that you can add instead of subtracting. So we get negative, sorry, I lost my square there, 6x squared plus 12x, bring down the minus 60. And x squared times negative 6 gives us the negative 6x squared. And notice if we change the signs on all of these, it gives us a remainder of 0. And then we could finish factoring our x squared minus x minus 6, as we did on the last example, to finish finding the zeros. And again, listing all of the zeros, we would have the 1 minus 3i, 1 plus 3i for the conjugate, and the 2 zeros we got from finishing factoring the trinomial.